very warm welcome once again. This is Shishir Mittal and we are bringing from Vyas Certification a beautiful series for you, NCERT discussion of chemistry. Today we have a topic from class 12th, and what is that topic? Yes, that topic is electrochemistry. The fabled, the feared and the enormous electrochemistry. Electro happens to be a very interesting topic in many respects. Why? Because first of all, it is a deeply conceptual topic. Students often are not very happy about electrochemistry because the reason is they often do not understand what is going on in electrochemistry. Failure to visualization, very simple thing, even as fundamental thing as substances are losing electrons, the other substance is gaining electrons, which way or in which direction is the electron traveling. It's not more than a 5 to 10 minute talk, but simply because at times this information is missing, this visualization is missing, electrochemistry happens to become a very dangerous topic. Today, our attempt is not only to discuss the NCERT electrochemistry, but also to demystify electrochemistry as far as I can via this discussion. Are you ready? There we go. Arrange the following metals in the order in which they displace each other from the solution of their salts. Now, you are supposed to arrange them in the order of their reactivity, the so-called activity series. Oh wow, and what is that? If you take a look, well, if you have copper, now copper happens to be a noble metal. That means copper ions very easily get reduced to copper, and copper is a little difficult to oxidize to copper plus 2. Amongst the remaining ones, magnesium is an S-block metal. S-block metals are most reactive and they give away electrons most easily. So can magnesium displace the other metal cations from their salt solutions? Easily. Wow. So the order in which they displace, well, magnesium most easily displaces everything. And then comes aluminium. And then comes zinc. And then iron, and last of all, copper. How did I write this? I remember a magical series called Electrochemical Series. And what is that series? Let me share the secret with you. It's hardly a secret, everybody knows it, but still, first of all, this is the answer. How do I get this answer? I get this answer from Electrochemical Series. Just before we wash our hands off this question, let me recount the series for you and give you 2 or 3 tips about the electrochemical series so that you're able to use this very effectively. First of all, the series. Oh wow, this is enormous series. Let me move myself away. If you wish, you can take a screenshot. This is the fabled electrochemical series, which in fact, if you have remembered this, you might need to write it down 5 to 10 times, but then ultimately you would come to remember, and this is a very useful series. Why? On this side, if you notice, on this side, metals are excellent reducing agents. So the most powerful reducing agent is lithium. Potassium is less, barium is lesser, strontium, calcium, sodium are successively less powerful as reducing agents, but nonetheless they are all good reducing agents, and the reducing power decreases. This is also the order of reducing power of metals. And this is something which we have used in solving this question. If you care to notice, we had magnesium, we had aluminium, we had zinc, then we had iron, and of course we had copper. So 5 in the grand series. All you have to do is just to pick them up, that's it. On this side we have excellent reducing agent, and on this side if you have non-metals and oxidizing power increases. If you go on this side, you find reducing power of metals decreases and oxidizing power of non-metals increases. So iodine is a non-metal and it is not that powerful an oxidizing agent. Bromine is more powerful, oxygen and chlorine are still more, and the most powerful oxidizing agent is fluorine at that end. So what do I have here? I have non-metals which are powerful oxidizing agents. Are only non-metals? Also we have metal ions. What do you mean by that? It means that gold ions. See, when we talk about electrochemical series, it is not just gold alone. What it means is gold is in contact with Au3+. How willing Au3+ is to get reduced to gold. So by this data you also get an idea whether gold can be easily oxidized to gold +3. The answer is no, it's a very, very poor reducing agent. Gold has absolutely no tendency to get oxidized. And in case you have gold cations, Au3+ ions, do they have a tendency to go back to gold? Yes, very much. And that is why they're called noble. Noble means that they don't like to stay as metal ions. They always go back to the nascent, the neutral metallic form with oxidation number 0, no charge, no load, no stress, nothing, right? So gold is noblest of all metals, accompanied by platinum maybe. Mercury and silver are also noble, but not as noble as gold and platinum, and copper is still less noble. But copper, silver, mercury, platinum, gold, all these 5 are called noble metals because they are least reactive of all metals, right? Right. One more caution. In a few books, you might find mercury located here before silver. Why is it and how come this mercury is here? There are 2 cases. One is mercurous ions being reduced to mercury, and then there is another case of mercuric ions being reduced to mercury. Is there a difference? Of course there is. What is the difference? Here. This is the one which I am using here. Mercuric ions being reduced to mercury, the location is this. In case you have mercurous being reduced to mercury, it would come just on this side of silver. They are more or less similar, but slightly they differ, and that is why you discover that you might get other series which might have shown a little bit of difference. But trust me, this is the most useful form of series. It is easiest to remember. It is easy, it's such a long series. It is still not as dirty as it could be. And yes, is it useful? It is very, very useful. So the first thing you should do is learn the series by heart. Done? Done. And there comes a numerical question which says, given the standard electrode potential of potassium ions to potassium is minus 2.93 volts, physically try to interpret it. What does it mean? It means that it is negative, that means it is not favorable, which means that potassium ions have absolutely no tendency to come back to potassium. Silver ions to silver is plus 0.8 volts, mercuric to mercury is 0.79 volts, and magnesium ions to magnesium is minus 2.37 volts. Please note, a lot of minus values. Cr3 plus to metallic chromium is minus 0.74 volts. Okay. Arrange these metals in their increasing order of reducing power. Reducing power, what does this mean? That means metals are reducing others. And what is reduction? Gain of electrons. Reducing power is if somebody gives you electrons so that you are reduced. If they can reduce others, then they themselves are called reducing agents. If they teach others, they are called teachers. If they reduce others, they are called reducing agents, right? So, in this case, we are not concerned with metal ions, but rather we are concerned with metals. If I have this reaction, K giving you K plus plus electron, since this electron is given to somebody else, potassium is acting as the reducing agent, and for this E naught value, what would be the E naught value? Let's say this is minus, no, since it is the opposite, is now plus 2.93 volts. Why you made it plus? This is reduction. Potassium ions to potassium. And standard reduction potential, see, standard electrode potential is usually SRP, it is reduction potential. And the way it is written also indicates reduction. Why? Potassium ions to potassium is minus 2.93, I reverse it. If I reverse it, I get plus 2.93 and of course the opposite reaction, right? Right. Then if we have magnesium, going to magnesium ions plus 2 electrons. E0 is plus 2.37 volts. So, potassium loves undergoing oxidation. It absolutely adores giving away electrons and it is very positive about it. Magnesium also loves it, but not as much. So, magnesium is not that good a reducing agent as compared to potassium, but both of them indeed are excellent reducing agents, as we just saw in the electrochemical series also some time back. Now, what about others? Well, let me pick chromium. Chromium metal, if it forms chromium plus 3 electrons, this E0 looks like plus 0.74 volts, which at least, although it is much lesser than other ones, but it's positive. If you look at the other ones, if you have mercury and silver, more or less very close, going to mercuric plus 2 electrons, Ag plus 2 electrons, you would find their E0s as minus 0.79, oh ugly, and minus 0.8, more ugly. Very close but still. So my dears, this is the increasing order of reducing power. Most powerful is potassium, less than that is magnesium, then chromium, then mercury, then silver. This is increasing order of reducing power. Done? Done. Depict the galvanic cell in which the reaction zinc solid plus 2Ag plus giving you zinc ions plus 2 silver takes place. Okay. And further show which of the electrodes is negatively charged, the carriers of electric current in the cell and individual reaction at each electrode. So we are supposed to construct a simple galvanic cell of what is called as metal-metal ion electrode, and we are supposed to discuss and explain that. That's a very beautiful and fundamental question, and this is one question, if you understand this properly, your initial fear of electrochemistry would be substantially reduced. Are you ready? There we begin. See, what I've drawn here is just to save time, I've pre-drawn it. It is a simple vessel in which I have some liquid, some solution and a rod. And what is this? If you have zinc and zinc ions, always remember, metal has to be kept dipping in the solution of its own ions. Its own ions, nobody else's ions. So if you have a zinc rod, then zinc rod has to be dipped in a solution of zinc ions. Silver ions and silver. So this has to be silver metal. Then this solution has to be Ag plus ions. Okay, very interesting. Now, what are these two? These two are called electrodes. One of them may be cathode and the other one anode. Which one is what? We'll see how to decide that. What is this in between? This is very interesting. This is something which is called as salt bridge. What is this salt bridge about? As you can see in the name, it's a bridge and it consists of salts. It is an inverted U-tube. U-tube is a different U-tube also. You are watching us on YouTube also probably, right? But then, this is an actual U-tube, physical U-tube made up of glass usually. You keep it inverted and you keep it filled with a solution. Which solution? The solution is of salts. Often it is KCl or KNO3 or NH4Cl or NH4NO3. Potassium or ammonium, chloride or nitrate. Something of that kind. And what is the role of this? And please note, if you just keep a solution and if you invert it, the solution is going to flow out. So what do? You actually fill it up. you actually fill it up with a gel. You take some gel, agar-agar gel, some kind of a gel, and you mix it with KCl or KNO3 and you fill in this. Even if you have gel, gel may not flow immediately, but gel would ultimately flow. So you put cotton plugs also here. What is cotton plugs? Cotton. You just take some cotton and stuff it so that everything does not tumble down or just slowly flow down. It doesn't happen, right? This is the initial arrangement. And what is the role of this salt bridge? It is a very crucial role. Ions from salt bridge can move into this as well as this vessel and make sure that each solution stays electrically neutral. Oh wow, is that the case? Yes. Is the circuit complete? Of course not. We have to join this, and just for the sake of enjoyment, we will attach a bulb also. Attaching a bulb makes sure that when the current is flowing, we can discover that a current is flowing. And the moment you attach a bulb, you would actually find that it begins to glow. Why? The cell is ready and it is functional. That is why. Okay, and what exactly is happening? So first of all, depict the galvanic cell. First portion is done. This is the galvanic cell. The second portion says, which of these electrodes is negatively charged? Carriers of the current are which ones? And the individual reactions. Now let us discuss them one by one. So first of all, we have to consider what are the reactions which occur at each electrode. Zinc and silver, if you compare them with respect to their positions in electrochemical series or reactivity series, you would discover that zinc has a stronger tendency to give away electrons as compared to silver. So zinc typically would function as anode. If you don't remember, let me repeat. What is anode? The electrode at which oxidation occurs is anode. So please don't remember anode as a positive or negative one. No, wherever oxidation occurs, that is anode. Oxidation is occurring, right? So this is anode. Wow, so this is anode. And wherever reduction occurs, that is cathode. So what happens here? Ag plus takes up electron and gets reduced to Ag. So this has to be cathode. But explain more clearly what is happening. See, the moment you dip a zinc rod in a zinc solution, suddenly zinc atoms become aware, oh my God, we have a solution. Now we are in a swimming pool. Now we are going to jump and we are going to swim and we are going to have fun. So what they do? Zinc atoms, chabak, 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 they actually start jumping and they start moving within the solution. But please remember, zinc metal atoms can't swim. So they leave their own electrons here. Oh my God. So these electrons, yes, they leave excess electrons on this rod. And zinc ions now begin to enter the solution as they like to swim. That's the way of nature. That is their nature. This is the way they function in nature. Right. So now this rod acquires a negative charge with respect to the solution. Right. And what happens at this end? The moment a silver rod is dipped in a solution of silver ions, suddenly, silver atoms are, they are sleepy by nature. They love to sleep. Ag plus ions, the moment they see the opportunity, they say, oh my God, there is a silver rod and we are also silver and they're also silver. So let's go and sleep. And they immediately run towards the rod and oh my God, now we would like to get deposited, we like to stick here. But the problem is, Ag plus ions are ions, they are not atoms. So what they do? They say that if somebody has extra electrons, we will eat your electrons and we become silver and dadam, we are going to stick on the rod and we are just going to sit happily. That is the attitude. Okay, so what happens is silver atoms start moving from solution and they start getting deposited on silver rod. Silver rod becomes thicker and fatter and zinc rod begins to dissolve and it becomes thinner and thinner. Fine. In the process, please note, this solution acquires positive charge and this solution acquires, because cations are lost from it, it acquires a net negative charge, the solution, please. And the rod, this rod becomes positive and this rod becomes negative. Oh wow, so that means in a galvanic cell, cathode is positive with respect to anode, which is negative? Yes. So we have written the individual reactions. We have talked about which electrode is negatively charged. Now about the current. That is most crucial. Please remember one rule. Electrons will travel only through metal. They will not flow through water, right? So, if these extra electrons are left out here, they are not very keen to jump in water. They can't swim. Electrons can't swim. So, these electrons, ting tadang, ting tadang, ting tadang, ting tadang, they enter, and in the process of entering from one end, and this is positively charged, and electrons are negatively charged. So, from minus, they tend to flow on this side, which is positive, where electrons are less. And as electrons flow, the bulbs glow. Oh, that's a poem. Yeah, kind of. So, as the current is established, the bulb begins to glow. You can say that, oh wow, this is functional. Yes, it is now functional. Isn't that lovely? That's very lovely. And as this is happening, as current is flowing continuously from one end to the other, one end to the other, one end to the other, which is fabulous, fantastic, there is one last problem left. This solution is becoming more and more negative, and this solution is becoming more and more positive. And this is where salt bridge kicks in. It says, I have potassium chloride. Say, for example, salt bridge has potassium chloride. Now, you will find that anions will start flowing in this direction. And cations within the bridge will start flowing in this direction, so that these cations can compensate the charge of extra anions in cathode, and these anions can compensate the charge of extra cations in anode. So ions begin to flow within the salt bridge. Yes, not electrons, but the carriers of current in the cell. In wire, the current carriers are electrons. Be very clear, the answer is in 2 sentences. In the external wire, the current carriers are electrons, but in the aqueous solutions and in the salt bridge, the current carriers are cations and anions. Both cations as well as anions. Which cations? All the cations can carry current, and all the anions also can carry current. Depends which one is being used at what point of time. That's it. This is the way it happens. So, slowly you might imagine that after some time all potassium and chloride ions would have gone away. That's okay. But as time passes, please note zinc ions will also enter. From this end, chloride ions or nitrate ions, whichever ions are the nitrate most probably, the nitrate ions will also enter. So, as they keep on entering, you will not be short of ions in the salt bridge. Initially, salt bridge uses its own ions, and as time passes, ions within the compartments also begin to enter salt bridge because they move slowly, so they take time to enter, and salt bridge is usually never short of ions. This is the construction of a galvanic cell as described here. And all this mechanism which I have told you, very simple, but it is rare that it is clearly communicated everywhere. If students don't understand this clearly, they always have a problem. And I hope you will not have it, because you would have understood this by now. In case you have a doubt, repeat this, listen to it once again, or twice or thrice, till you get a knack of it, and then electrochemistry will be easy. Calculate the standard cell potentials of galvanic cell in which the following reactions take place. Chromium, cadmium ions are giving you chromium ions plus cadmium. Ferrous with Ag plus is giving you ferric plus silver. अब ये आपको reactions दिए गए हैं. Calculate the delta G naught and equilibrium constant of the reactions. How do we do this? Well, actually we would need some data. There's no data given except for the reactions. But actually if you look in NCERT, there is a table. Yes. And if you look at this table, a lot of E naught values are given for the half reactions, and this is the table you would need to consult. So, what all has been asked? Let's take a look. It is chromium, cadmium, ferrous, ferric and silver. So, do we see any chromium, cadmium, ferrous, ferric, silver here? Let's take a look. We have, well, ferric to ferrous. Ferric to ferrous, the standard reduction potential, this is 0.77, and Ag plus to Ag, it is 0.8. So, we have two data. Fine. Do we have more? Yes. We need for chromium and we need for cadmium. For chromium and cadmium, chromium is here. How much is that? Chromium, the SRP is minus 0.74. Okay. And for cadmium, that would be, let's see if cadmium is somewhere offered. Otherwise, we would need to find out from a separate source. It doesn't look like as if cadmium is very much included here, but we would need the data on cadmium for the E naught value. But let's solve with what we have. So from that table, we have noted these values. SRP of Ag plus to Ag, ferric to ferrous, Cr3 plus to Cr. Cadmium is missing in that table, but we would need the value for. So I have taken this value from an independent source. Please note, in absence of this value, you would not be able to solve this problem. This is a data which should be given in the question. Now, let's take a look at part 1. Part 1 says, the reaction is chromium is undergoing oxidation and cadmium is undergoing reduction. And whichever undergoes oxidation is anode and whichever undergoes reduction is cathode. Wow. So how do I find out E naught cell? I can say E naught cell is E naught cathode minus E naught anode. Reduction potential of cathode, and what is that? Cadmium 2 plus to cadmium, that is how much? Minus 0.4 volts. Minus of reduction potential of anode. Now anode, actually what happens? Actually oxidation happens at anode. But then why are we writing minus? Because if we negate it, if we put a minus sign, that means we are reversing the reduction reaction and we are actually converting this to oxidation reaction. And oxidation is something which actually happens at anode. So that is minus of 0.74, which is plus 0.74 minus 0.4, and how much that is? Plus 0.34 volts. So E naught cell, I have just calculated E naught cell by the formula. It is simply 0.34 volts. And we know very well the reaction is what? It is Cd2 plus 2 electron giving you Cd. So N, the number of electrons, the value is 2. And delta G naught is minus NF E naught. Oh no, N is not, I mean for this half reaction, N is 2, that's fine. But then we have a bigger reaction, we have this kind of a reaction. So for one cadmium, the value of N is 2, and there are 3 cadmiums, that means a total of 6 electrons are being exchanged. So N, the value of N now becomes 3 into 2, which is 6 for this reaction. Oh, you have confused us. Let me repeat, what is N? N is the number of electrons involved in the half reaction or full reaction, depending upon whether you are writing it for half reaction or full reaction. Now, when you are writing it for a cell reaction is a full reaction. So, you are supposed to write N for a full cell. And how much is that? Total number of electrons lost by anode or gained by cathode as per the balanced reaction. One chromium loses 3 electrons, 2 chromiums lose 6. N key value is 6. Or if you look at cadmium, one cadmium gains 2 electrons, 3 cadmiums gain 6 electrons. Whichever way you look, the value of N comes out to be 6. So this is minus 6.96500 coulombs per mole into E naught. How much is E naught? That is 0.34 volts. Oh my God. That's it. What do? We just calculate. I'll do that for you, of course, but then this is delta G naught. What about equilibrium constant? Delta G naught is also equal to minus RT ln K. Oh my God. So can we find out K from here? Of course we can. And what is that K? Ln K, yeah, log to the base 10 of K is minus 1 upon 2.303 RT into delta G naught. And delta G naught is nothing but minus NF E naught. So this is minus NF E naught upon 2.303 RT. Oh, that looks ugly. That's not ugly. It's beautiful. Temperature has not been mentioned, but since nothing has been mentioned, let us be shameless enough to take temperature as 298 Kelvin, because this is usually what is done. If nothing has been mentioned, we just assume it to be 25 degrees Celsius, 1 atmosphere. Okay, assuming that, If you substitute these values here, n of course is 6, whatever. And we have this ready calculation with us anyways in the form of formula. Delta G naught is minus NF E naught. If you substitute this value of all this funny thing, 2.303 R, T, F, etc., etc., this is, you remember that number 0.0591? Yeah, that is the calculation which you actually get. It is useful to remember that simply because it does not remain as ugly as that. So this is minus 6 times, of course, E naught by, so this is minus of delta G naught, that means plus. Delta G naught is minus NF E naught, and minus of minus becomes plus here. There was a silly mistake, we have just corrected that. So this is 6 E naught by, the whole drama comes out to be 0.0591. Oh my God. What do we do? E naught, we are aware it is 0.34. So this is 6 into 0.34 by 0.0591. Let's calculate that, and then when we do the antilog, we get the value of K. If you take a look at the answers, it's a little dirty calculation, but it comes out to be how much? Well, you get your delta G naught value as 196.86 kilojoules per mole. Don't you forget, E naught cell was 0.34 volts. K, if you calculate, it's around, you can very well guess. See, I can tell you how to get the order of magnitude. Now, this is a very accurate calculation. If you're interested, I can also guide you with rough calculations. But then, when you're taking antilogs, please remember, the error becomes greatly enhanced in case you are taking antilogs. So, that becomes a bit dangerous. But let's see, 0.0591, if I approximate this as 0.06. Now, I have raised this a little. So, 0.34. Now, 0.001, I have increased it by 0.0009. Fine. So, what happens here? Maybe this might be slightly enhanced. Instead of 0.34, it could be 0.341 or 342, something of that kind. But then if I do this, I get this value as 34 or 34 point something. 34 point something. This is what I get. And if I take antilog, one thing I am sure that it is something. See, because this is mantissa. So whatever antilog comes, that antilog would be here, and that is very sensitive to what the kind of approximation you have made. But then 10 raised to 34, this is very clear. You can get 10 to the power 34 clearly from this approximate calculation also. So it is a careful, it's a very good method for cross checking. In case you get a multiple choice question like ABCD options, and if there is only one option with 10 to power 34, you don't have to calculate accurately also. You could have calculated like this also. But otherwise, please remember, whenever you have to take antilog, it becomes highly sensitive to approximations. So even if you make a very minor mistake here, it would be highly magnified on taking antilogs. So you have to be careful, and you have to be very accurate when you are calculating this portion, right? This was first part. What about the second part? It's a very similar thing. You should do it now. We have done it. Well, let's check. Let me also solve it for you and show how it is done. Now we are solving the second part, which says ferrous is oxidized to ferric. This is anode. And Ag plus is reduced to Ag, which is cathode. Well, pretty lovely. We are having SRP values of both, and E naught cell is E naught cathode minus E naught anode. Cathode is silver. So that is 0.8 minus 0.77. This is 0.03 volts. That is pretty small, yes. Nonetheless, what about the value of N? If you care to just see, the value of N is simply 1. Why? Because Ag plus to Ag, 1 electron, ferrous to ferric, 1 electron only. So, delta G naught, which is minus NF E naught, which is minus 1 into F, 96500 coulombs per mole, into E naught is 0.03 volts. Volts into coulomb is joules, so joules per mole. And if this is 96.512. Sorry, 965 into 3. If I just, this so many joules per mole. How much would that come out to be? Let's multiply and see. 5 3s are 15, 18, 19, 6 3s are 27, 28. So I get 2895 or 2.895 kilojoules per mole. That's a reasonably small value. Yes, it has reduced. It is 2.9 kilojoules per mole roughly. This is the value of course, with the negative sign. So minus 2.9 kilojoules per mole. What about value of K? Let's solve that out. That's not difficult. We have just seen log to the base 10 of K is N into E naught upon 0.0591. We just did that, right? So how much is N? N is 1. What about E naught? E naught is 0.03 volts up by 0.0591. How much does that come out to be? That is 1 by 1.29, 9 is 27, 97. That's, well, not very encouraging, but whatever the number looks like. When we take antilog, K comes out to be, we can calculate this, carry out calculations, take the antilog. And the antilog gives a value of 3.22. Oh wow, that's it, that's it. This is the equilibrium constant, which shows that slightly it is pushed in the forward direction. And I mean, both the species have roughly same tendency to exist. This was the question. And this is a question about Nernst equation. What does Nernst equation tell you? Actually, you might be able to calculate E naught cell, but if there are cases in which we have non-standard concentrations, that means concentrations which are not 1 molar or pressures, partial pressures which are not 1 bar or 1 atmosphere. In that case, if you record certain volume of whatever would be the EMF of the cell, that would not be the standard EMF. It might be different. And this EMF of non-standard cell can be calculated using an equation called Nernst equation. What does it say? It says, first of all, I'll just give you a very good example. Let's first write down this case for first question. Magnesium, magnesium ions, copper. Now what is anode reaction? Anode reaction is magnesium is giving me Mg2 plus 2 electrons. And at cathode, copper ions gain those 2 electrons and they give you copper. If I add up, I have Mg plus Cu2 plus aqueous giving you Cu metal plus Mg2 plus aqueous. Is that all right? Yes, of course it is. It's great. It's absolutely great. Now when I have this is the cell reaction, write down. Can I write down the reaction quotient Q? You remember equilibrium constants and reaction quotients. If you just assume this to be reversible reaction, what would be the reaction quotient Q? Q would be concentration of magnesium ions divided by concentration of copper ions, right? And in case it is a standard cell, copper and magnesium ions both would be 1 molar each and Q would be equal to 1. But in case Q is not 1, for example, in this case, concentration of magnesium ion is 10 to the minus 3 molar divided by 0.0001, copper ions is 10 to the minus 4 molar. Oh my God. So this is 10 actually. Yes, it's 10. Now, this is the calculation of Q. How did I get Q? First I wrote down, looking at the cell, I wrote down anode reaction and cathode reaction. I add the reactions so that electrons cancel, and the number of electrons cancelled represents N, and I get the overall cell reaction. From this cell reaction, I write down, see, for solids are excluded. They are not a part of a game. Liquids, the solution, the aqueous solution species and the gases, they are used in writing down the reaction quotient Q, right? So we wrote down Q. How did I get this? By writing them. How did I get them? By looking at 1, anode and cathode. And once I've got Q, I've got N, all I have to do is substitute N's Nernst equation. Do I need something else? Yes, I would need E naught cell also. But before that, let me write down Nernst equation for you. It says E cell is equal to E naught cell minus 0.0591 upon N log to the base 10 of Q. Oh my God, what is 0.0591? This is RT upon F. If you take R, F and T, temperature is 298 Kelvin, this is the value you get. You substitute that at 2.303 also of course there, because ln has been converted to log. This is Nernst equation. Fascinating. I have N, I have Q. The only thing I need is E naught cell. Can I get that? Of course I can get that. Why? I mean, what is E naught cell? For this case, E naught cell is equal to E naught cathode minus E naught anode. Cathode is copper ions to copper. E naught of copper ions to copper minus E naught of magnesium ions to magnesium. How much would that be? Well, let's take a look. Copper ions to copper is 0.34 volts. It is not given in the question paper or in the problem here, but NCERT has given you already a list and that contains that number. This is 0.34 volts minus the value of magnesium ion E naught. You might need to check that, right? And once we have that, what do? E naught cell we have 0.0591 by 2 log to the base 10 of Q. Now Q is 10, so log 10 is 1. We just substitute that and we get the answer. Magnesium ions के लिए आप देखोगे तो value है -2.37. Oh my God, that's pretty high. Yes. So how much is this? This is 2.6. No, not 6 also. This is 2.71 volts. That's pretty high. Yes, that's pretty good. तो E naught cell है 2.71 वोल्ट और E cell कितना हो जाएगा? इसको यहाँ सब्स्टिट्यूट करते हैं और निकाल लेते हैं. कैसे? आइए देखिए. This is 2.71 minus 0.0591 upon 2. Log to the base 10 of Q, log 10 is 1 into 1. 0.0591 अगर आपको थोड़ा अगली लगता हो, एक क्षण के लिए 0.06 मान लीजिए, 0.06 upon 2, 0.03, तो आएगा 2.71 में से तो 2.68 volts. This would come out to be 2.68 volts. Is that fine? Yes. This is the first part. ऐसे ही हम करेंगे second, third or fourth. Let's begin. Second part, if you look at, it says iron to ferrous. This is anode and hydrogen and H plus. That is cathode. Very interesting. Let's take a look. Now first, what is the way to solve this? First of all, write down the reactions at anode and cathode. So left side is anode. Anode is iron getting oxidized to ferrous plus 2 electrons. And 2H plus 2 electrons gives you hydrogen. If you add up, you get iron plus 2H plus gives you ferrous plus hydrogen. This is the overall cell reaction, right? How do we write down reaction quotient and N? We cancel 2 electrons, so N is equal to 2. What about the reaction quotient? Can we write down that? Of course we can. How about Q? Q is products. Product is ferrous upon H plus ka square. Square of H plus 2H plus. Solid iron is skipped and hydrogen is gaseous. What about gases? Into partial pressure of hydrogen. Wow. So we write down partial pressure for gases and concentration for solutions? Yes. Solids are simply neglected drop. We don't mention them at all. Okay, well, that sounds simple enough. Now, could we calculate reaction quotient Q? I guess we can. Ferrous ions are 0.001 molar each. This is 0.001 molar divided by H plus is 1 molar. 1 square into partial pressure of hydrogen is 1 atmosphere or 1 bar, which is again 1. Please remember, partial pressure is to be taken in atmospheres or bars. Both of them are reasonably close, while the concentration has to be taken in molarity, right? How much is this? This comes out to be 10 to the minus 3. So Q comes out to be 10 to the minus 3 or log Q. What about log of Q? Log of Q would be minus 3. In Nernst equation, we would come across log Q, so please note. What about E naught cell? Can we calculate E naught cell? Of course we can. E naught cell is E naught cathode minus E naught anode. What about cathode? Standard hydrogen electrode has E naught cell 0, yeah, half cell. And what about anode? Anode is iron to ferrous minus 0.45 volt. If you check the chart given in NCERT for SRP values, that comes out to be 0.45 volts. That's beautiful. That is E naught cell. And E cell would be equal to E naught minus 0.0591 upon N log to the base 10 of Q. Now log 10Q is minus 3. N is 2 and 0.0591, this is too ugly a number. If we approximate this by 0.06, not very bad. What do I get? I get 0.45. Now minus 0.06 by 2 is 0.03. 0.09, so that makes it 0.54 volts. Oh wow, 0.54 volts. Yes, that would be the EMF of second cell. But don't you forget, this is approximate because we assume 0.06 instead of 0.591. If you do it more accurately, the actual value comes out to be 0.528 volts. And how do I get this? Use accurate value. I just found out approximate. This was an approximate value which I used. If you wish to make it more accurate, this is what you are going to land up with. Done? Done. And there comes now the third option, which contains tin as well as hydrogen electrode. And in this case, hydrogen electrode is no longer standard. H plus ions have now a different concentration. How shall we do it? Let's do that. First of all, write down the reaction. Now, students consider Nernst equation difficult. Why? Because they skip the first step. And what is the first step? Writing the cell reaction. If you are good enough, if you just spend 30 seconds extra and write down the cell reaction properly, you would never find it troublesome. Also, we don't know how to write down cell reaction. I'll tell you, it's very simple. See, left side is anode, so write down anode. Now, first put an arrow, tin, solid, is giving you stannous ions. Just write down oxidation reaction. That is simple, of course. What about cathode? 2H plus aqueous plus 2 electrons is giving me hydrogen gas. Okay. Could I add this? Of course you can. Tin solid plus 2H plus aqueous gives us stannous ions aqueous plus hydrogen gas. Can you write down the reaction quotient? Yes, we can. Q is concentration of stannous into partial pressure of hydrogen by concentration of H plus to the power 2. Tin being solid is dropped. Now hydrogen, many times in different guides you will see they will skip the partial pressure of hydrogen. Please remember, partial pressure of gases should not be skipped. In NCERT, unfortunately, they have, in such cases where concentration and pressure both are present, they have assumed that only one of them varies. So even if you skip it, it doesn't matter. But accurately, this is the way you have to do this, right? And can I calculate this? Of course I can. What about stannous ions? Stannous ions are 0.05 molar and H plus ions are 0.02 squared, right? And then you have hydrogen, which is 1. Could we calculate that? Yes, of course we can. This is 5 by 2 into 50. 5 by 2 into 50, which is 5 into 25, which is 125. Oh my God. So this reaction quotient comes out to be 125? Yes, it does. So far so good. Now, let's substitute in Nernst equation. We'll need E naught cell also. What is E naught cell? I'll not write down the formula third time. We have written it twice already. E naught of cathode minus E naught anode. Now, what is cathode? Cathode is tin to stannous or stannous to tin. That is minus 0.14. Cathode is 0. This is cathode. Cathode is 0. Minus anode is minus 0.14 volts. So this comes out to be 0.14 volts. Okay, beautiful. Could we substitute? Yes, we can. E cell will be E naught cell minus 0.0591 upon N. N is 2 into log to the base 10 of Q. Q is 125. horrible. What is log of 125? We will have to check. We'll check and see. Actually, instead of 125, if you write down 1000 by 8. These are the logarithms probably I remember. How do I remember? I'll solve it for you and show you. Log of 1000 by 8 is log of 1000 minus log of 8, log of 10 raised to 3 minus log of 2 raised to 3. Okay, that's lovely. How much is that? Log of 10 is 1, log of 2 is 0.3010. This is 3 times 0.7 approximately. If you subtract and all, it's around 3 into 0.7, whatever that comes out to be. So this is 0.14 minus 0.06. I'll just give you first approximation. 0.06 by 2 is 0.03 into 3 into 0.7. Let me see what does this give me. 3 into 3 is 0.09, 9 7s are 63. So that would make it 0.14 minus point, and how much is that? How many zeros? 0.09, 0.063. Sorry. Could I subtract that? Of course I can. 140, if you take away 63. From 0.14, if I take away 0.6, that is 0.08. 0.08. That's close to 0.08 volts actually. Because please remember, this is a slightly bigger value. We have assumed 0.06 to be subtracted while it is actually 0.0591 only. So I'll obtain close to this, somewhere 0.079 volts or something, which can be approximated as 0.08 volts, which is fine. That is the answer for third question. And there comes the fourth one. Oh my God, with a bang. And this time we have a non-metal. Bromide ions getting oxidized to bromine. Wow. Let's write down the reaction. Bromide ions getting oxidized to bromine and releasing electrons. On the contrary, who's getting reduced? Now, reduction apparently is with H plus ions. H plus ions are getting reduced to hydrogen gas. That seems awfully negative and bad. Let's take a look. It is 2 times Br minus plus 2 times H plus, giving you Br2. Br2 is of course liquid, plus hydrogen, which is gaseous. Now please note, bromine liquid is a pure liquid. It is not something which is soluble in water much. So if they are clearly writing Br2 liquid, it stays as Br2 liquid, and pure liquids and pure solids are not considered while writing reaction quotient Q. So Q would be simply how much? Partial pressure of H2 gas, which is actually 1 bar, divided by concentration of H plus square Br minus square. Oh my God, and how much is that? That is 1 bar divided by how much is H plus? 0.03 and Br minus 0.01. So 0.03, 0.01. Fancy. What would that be? This is 10 raised to 4 upon 9. Oh, ugly. Can we take log? Yes. So log 10Q, because we often need this, is log of 10 raised to 4 by 9, which is log of 10 raised to 4 minus log of 3 square. 9 is 3 square. Power can come out. 4 log 10. Sorry. And log of 10 is 1. This is 4 minus log of 3. 2 times log 3. Log 3 is 0.4771. 0.4771 into 2. This is 0.9542. Cheap and ugly, whatever it comes out to be. How much is this? This is 3. God save me, whatever, 3.0458. This is the value of Q. Why have you calculated Q? I'm also supposed to calculate E naught. Let me calculate E naught cell also, which is E naught cathode. How much is that? 0. Minus E naught anode. Now bromine to Br minus. Reduction potential of bromine is 1.09 volts. How do you discover this? It is in the chart given in electrochemical series of NCERT. You can see the value from there. What about exam? If it is asked in exam, E naught values will have to be given to you. Obviously, you cannot discover them on your own automatically. So this is, now reduction potential is 1.09 volts. So oxidation potential, now this comes out to be minus, this is minus 1.09 volts. Horrible. E naught cell is so negative. That means this doesn't look like a spontaneous reaction. Of course, it is not a spontaneous reaction, but we are just supposed to find E naught cell, that's it. And E cell, so we'll just find that, even if it's negative. So, E cell is E naught cell minus 1.09 minus 0.0591 upon 2 log to the base 10 of Q, oh my god, and that is 3.046. This is 3.046. Let me make more hectic calculation. This is minus 1.09, yes, and minus 0.0591, God save me, into 1.523. Lovely. So loving, so delicate. It is getting more and more negative. And this is minus 1.298 volts, roughly minus 1.3 volts. This would be E cell for the final and the fourth part. Well, let's take a look at this question which says, in the button cells widely used in watches and other devices, the following reaction takes place. And you have a reaction. Determine delta G naught and E naught for the reaction. It's a lovely question with all possible characteristics of NCERT. What are the characteristics? Being illogical, being unreasonable, and trying to appear fascinating without actually sometimes it can get disgusting. It's a very beautiful question which has been ruined simply because they have not cared to give you a KSP value. And that value is not present, and within the NCERT text also it is not very easily locatable. So ideally they should have printed that value. I am adding this value also. Without this additional value you would not be able to solve this question, mark my words. This data should be a part of question which should be given. Oh, if it is not given, then it is stupidity. It is not some glamour or some fascinating aspect of NCERT. But nonetheless, I am giving this to you. Add this, and now this becomes a very beautiful question. Now let's try to solve this. Right? There we are. What do we do? First we write down the cell reaction. Well, anode, yes, we know how do we write down anode. Let's try anode. Zinc undergoes oxidation to give you zinc ions plus 2 electrons. That is so lovely. What about cathode? Had 2 Ag plus ions, accepted 2 electrons to give me Ag. That would have been great, but I don't have free Ag plus ions. As a matter of fact, I would need to consider another solubility equilibrium. And equilibrium constant for this is nothing but KSP here. Oh wow. So what do? I have 3 reactions. If I add them up, I would get overall reaction. And what is that? Let me just add and show you. Well, as I add them up, electrons do cancel. What else cancels up? You have 2 times Ag, and Ag plus ions also can be cancelled out, that's fine. And you get zinc solid plus Ag2O solid plus H2O liquid, giving you zinc ions aqueous plus 2 times OH minus aqueous plus 2 times silver. This is exactly the same reaction. Oh wow, so we have broken down the cell reaction into 3 components. Yes, these 2 reactions occur at cathode and this actually occurs at anode. Let me call this reaction 1, this reaction 2, and this as reaction number 3. Why is it? It is simply because I have to find out delta G naught for the overall reaction and E naught cell for overall reaction. Now delta G naught for overall cell, as you can see, Delta G is an extensive quantity. If I add up 3 reactions, the delta G naughts of 3 reactions also add up. If that is the case, I have delta G1 naught plus delta G2 naught plus delta G3 naught. Is that the case? Yes. And how much would that be? Well, delta G1 naught plus G2 naught is simply if you add up only this much. If you add this, actually this looks like a different cell altogether. See, the Velen is the third equation, the KSP equation, which is the new addition. Do I know delta G for this? For any equilibrium, I know. For a reaction, delta G is minus RT ln K. So could I say that delta G3 naught alone, mark my words, be very careful, only this much is minus RT ln KSP. Okay, so I know delta G3 naught. Yes. Do I know delta G1 naught and delta G2 naught? Well, actually I can discover them. How? If you just add this much, you get a different cell. Can I just scribble down the cell here in a different ink so that it becomes visible to you? I believe I can. It is going to be zinc plus 2 times Ag plus, giving you Zn2 plus 2 times Ag. Now this is a very regular metal ion electrode, the cell made by metal ion electrodes. And for this cell, E0 cell is E0 cathode minus E0 anode. Now cathode is Ag plus 2 Ag, which is 0.8 volts. How do I get, how do I get this 0.8 volts? From that fabled electrochemical series chart present in NCERT. And what about E0 anode? E0 anode is minus 0.76 volts. The minus of minus 0.76 volts, which is 1.56 volts. So only for 1 plus 2, I know E0 cell. And I also know a relationship. Delta G naught is minus NF E naught. So delta G1 plus delta G2 naught, this will be equal to minus NF E naught. E naught of this cell. In this cell, Ag2O is not there. Please note, in the original question, silver is present as Ag2O, and in our 1 plus 2 cell, silver is a routine Ag plus aqueous. It is not Ag2O, which is different. So this is minus NFE naught minus RT ln KSP. Is that the case? Yes. Could I calculate that? Of course I can calculate that. All I need to do is substitute. How much is N? The number of electrons which cancel is 2. So this is minus 2 into 96500 into 1.56. E naught cell is 1.56. Please note volts. So many joules per mole. Please don't forget to convert this into kilojoules per mole. Minus 2.303. R is 8.314 joules per mole Kelvin. Temperature is 298 Kelvin. Log of KSP, log of this dirty thing, multiplied by log of 3.72. God save me, into 10 is to minus 16. Fancy. What does all this exercise give me? I get delta G naught cell. All you need to do is now to substitute and calculate. Fanciful. And what does it come out to be? Minus 213.04 kilojoules per mole. This is delta G naught cell. Oh my God, that's a dirty calculation. It is one dirty calculation, but yes, you do get the answer. And this delta G naught, once you have got this, you can say this is also minus NF E naught. N is 2, F is 96500. Can you calculate E naught cell easily? And this E naught cell comes out to be 1.1 volts. Substitute, calculate, and get the answer. This is the correct solution to this question.